Hello, and thank you for attending this third and final presentations on flocculants. This one is on special applications with flocculants, and we'll get into that a little bit. So far, we've done two other parts of this three-part series. Our first presentation that you can go back and watch if you're not familiar with polyacrylamides is Introduction to Flocculants. And then the second part of this was a use of flocculants for erosion control and stormwater treatment. And now what we'll be talking about today are some lesser known but equally effective uses and applications for the anionic polyacrylamides that we have been discussing for the first part of this series. So what we'll start is a very brief flocculant introduction. Again, if you want to learn more about flocculants, specifically anionic polyacrylamide, I would urge you to go watch the other two posted presentations. And then what we're going to talk about specifically today are using the anionic PAM flocculants for metal treatment, nutrient removal for pond and lake management, sediment management, demucking and thickening up sediments, use for dust control, as well as some applications of pH and chlorine that we're not necessarily using the flocculants to do that, but we're using it as a special kind of mechanism in that. So with that, we'll go ahead and get started. First, again, the type of polymers that we're talking about in all of these applications and all three parts of this series are anionic polyacrylamide. Again, a polyacrylamide is a high molecular weight polymer. It's a very long linear chain. The reason we use anionic polyacrylamides is because it's the most widely used polymer for stormwater treatment and across the United States and multiple other countries, and that's because it's highly effective and it's also very safe for fish and aquatic organisms. Again, the charge of that polymer is very important for its safety, and the anionic forms of the polymer are the ones that are safe for aquatic organisms and the only ones that we use out in these kind of passive applications out in the open environment. There are different forms and types of polyacrylamide. When it's made, it looks like a granular or powder, and that's the silt stop, and that's used for both water treatment and erosion control, and you'll see some of the other applications that we are using it for today. We take that granular form and blends of those granular polymers and combine them and hydrate them into a solid form that you'll see in the two pictures on the right-hand side. And those are used specifically for water treatment. Those are called floc logs and pond logs. And then there is also a concentrated liquid emulsion form of the anionic PAM. And that is primarily used for terrestrial applications because the emulsifiers in there are not really suitable for passive water treatment, so we use that for erosion and sediment control. How the polymer works, again, it's activated when it's wet. It's kind of like a ball of yarn. This long polymer chain unwinds. It has many charge points along the chain that are able to bind to particulate. If we're using it for erosion control, that long polymer chain is binding those soil particles on the soil surface so it doesn't run off during rain events, so it helps with erosion. And in water treatment, we are using it, that same process works by binding suspended particles in the water column like sediment and metals, pulls them into these bigger, larger flocks or agglomerates that we can then settle out of the water or capture. Again, the primary benefits for erosion and sediment control with the PAM is we don't typically use it alone. Most of the time we're using the PAM with other erosion control best management practices, and the benefit of using anionic PAM, both the liquid and the granular, is it helps us bind the soil, seed, and fertilizer in place. It helps with quicker vegetation growth and establishment, increases permeability of that top layer of soil so water can infiltrate better, improves soil structure, stops soil loss, and improves runoff clarity. So a lot of benefits in adding this with our erosion control BMPs. And again, for water treatment, we talked about the flocculant fundamentals of how to make these materials work for water treatment in the previous presentation. And again, it has to be in flowing water. must be the right formulation, have to have that 30+ seconds of mixing and reaction, and have to collect those flocks once we form them. So again, those 5 fundamentals: formulation, dosage, we want to use the right amount, not too much, not too little, enough mixing quality, we want vigorous mixing. We a lot of times use other types of BMPs to improve our mixing quality, and we also want the right reaction time, so how long we mix the water and the flocculant, and of course particle capture. So as long as we do all of those things, we're going to be effective in water treatment. And that's not just for sediment, which is what we've been focusing on for the last 2 hours in this series. What we're going to be talking about today are some other particulate and contaminants that we're able to target. So when we're after clays and suspended sediments, we're often looking at 90 to 95+% removal. For metals, anionic polyacrylamides are widely used in mining, wastewater treatment, and they're very effective at removing metals. And so oftentimes it depends on which type of metal we're targeting. Just like with soils and waters, we need to be doing site-specific testing to know that we're taking out what we're after. And that is going to be 60 to 90% on average when we're doing metal treatments. And we can also handle quite a bit of phosphorus. So depending on whether it's particulate or dissolved, we can often remove around 60 to 70% of total phosphorus as well. So with that, we've kind of went through, again, those flocculant fundamentals. They're still going to come into play no matter what type of particulate we're trying to remove. We still have to get those flocculant fundamentals. And that's very true for metal treatment. So the first metal treatment, I just want to start by going through a few examples of how this was used. Again, the same process of how we remove sediment is how we remove metals. The only thing that's different is, again, our sample analysis or our sample procedure is going to be a little bit different for metals. When we analyze a sample to determine the right formulation to remove turbidity from water, we can often, again, we just use a general measure of turbidity. When we do metals, oftentimes the specific type of metal that the concern is about, we need to make sure that we're able to target that metal. So when we do our sample analysis, we'll do the treatment and we will send the metals out to be analyzed to ensure that our post-treatment sample is meeting the standards that we're trying to meet. And so same process, but the design and planning and sample procedure is slightly different for metals. So with that out of the way, the project that I wanted to kind of highlight, this was called Clover Bar Ravine. It was in Canada. The issues with this project specifically is they had metal and TSS contamination. This was an industrial area. They had a lot of non-point source runoff. It was in Edmonton, Canada, and this contamination was entering a fish-bearing stream, so they needed a very environmentally friendly solution. Again, that's one of the key benefits of using anionic PAM is that it is very safe for sensitive aquatic organisms. In many areas, we are not allowed to use PAM specifically in natural water bodies. Some places we are. So this example, we put the flocculant directly into a natural stream. You certainly check with your state or your local regulations to make sure that you're using the flocculants in what's allowed in your area and applying for any permits that you might need to put these in waters of the state. In this project specifically, again, we were using this directly in the stream with permission. So the flocculants, we tested this sample ahead of time, and we determined that the 706B and 703D number 3 floc log were most effective for removing TSS as well as a kind of a wide range of metals in this specific sample. Again, we installed these directly in the stream channel. And you can see in the bottom picture, since this was a live stream channel, it wasn't entering a sediment basin, there wasn't a really great area to settle those flocculated particulates. And so we lined the channel with the biodegradable natural jute matting and then strung some jute curtains downstream of that to collect the floc that was created during this project. This treatment was in place for 3 years. We measured before and after metal and TSS. Removal efficiency varied by metal, and this is what we typically see when we do metal treatments. So this is kind of highlights why we want to test if we're targeting a specific metal. We want to test ahead of time to make sure that we can get it, because we want to use the right formulation of polymer that's going to work for that specific metal. And again, that removal efficiency could go anywhere from no reaction to 95%. So we want to test ahead of time to make sure we get the right polymer. The average decrease is usually around 80% for the metals. So you can see just in general with the water clarity and TSS, the top picture compared to the bottom was very successful in our treatment of this site. The metals that we were targeting, pretty common: aluminum, copper, iron, lead, nickel, zinc, and of course total suspended solids. We saw a decrease in all of these. Again, that range varied. We'll look at the removal efficiencies here. So they varied by year and also by metal. And again, anywhere from around 50% to 95% was the removal efficiencies that we were seeing for these targeted constituents, with an average of the metals around 80%. Another really great metal example was another Canadian application. This was also in Edmonton, Canada. This was an aggregate washing facility. They were using the local river water in their wash operations, and then after treatment of that water or settling of the solids, they were returning that water back to the river. So this was only open during the summer months. Their existing pollution treatment consisted of 4 settling ponds that had about 20 acres of area and a 7-day retention time before the 4 ponds. And again, that discharged back to the river. The pollutants of concern, just like the previous, was total suspended solids and metals. The turbidity varied depending on the time of year. And what we were concerned with this project, just like the previous one, is that we were again dealing with a fish-bearing stream with quite a few different species. And again, the beauty of the anionic PAM is that it's safe for sensitive aquatic organisms. And we weren't discharging the polymer into the water, but we wanted to make sure that, if there was any, if anything had happened, or if there was any escapement of the polymer, that it wasn't going to cause any harm. This project was also particularly interesting because just like the anionic PAM can bind to metals, it really likes calcium as well. And so in hard water situations, like it was at this project, that calcium is, attracted to the anionic PAM, and it started to bind to the outsides of the logs that we originally, or the flock logs we were originally going to use, in forming kind of a hard crust. So what we did is we were able to kind of tweak the formulation and come up with a new, one of our most commonly used flock logs called the 703D number 3. So that's something that we can do at Applied Polymer Systems. Is we don't have a one size fits all. We can adjust our formulations and match the polymers to make sure that it works for the specific water chemistry in the soil. And so we created a new polymer or a new flock log that held up to specifically hard waters. And so this new formulation is what we used in this project, called the 703D number 3 flock log. The way we utilized it is we put in what we call a baffle grid mixing system. And it's essentially a way to get a lot of mixing and reaction in a small area. And so we installed this mixing system with the flock logs, which would be those kind of blue blocks there, between ponds 2 and 3. And with the idea that we would be settling the flocculated water or the flocculated particulate from this baffle grid mixing system in the 3rd pond. So you can see the logs that are attached via those rebar in this baffle grid mixing system. So this again is a really great way to get additional mixing and reaction time when we don't have a lot of linear space or long channels to utilize. So we had a really great results with the turbidity. So ponds 1 and 2, we had a significant decrease after the 2nd pond, where we had our baffle grid mixing system. After our flocculant treatment, the fourth pond really didn't add any additional treatment. So the flock logs between ponds 2 and 3 were really effective, and it kind of varied by the year, but the downstream after the flock log treatment was effective in decreasing the TSS. So again, the discharge water quality was significantly improved. We decreased the turbidity and the TSS. We also decreased metal concentrations. Again, that average was around 80% depending on what type of metal. I have that chart in there. I apologize for that. If anybody wants to look at the metal slide from that, please feel free to reach out. My contact information will be at the end of this presentation. So the polymer formulation in this one, again, we created a new formulation that was going to work well with this site's water chemistry, and we really didn't even, the space that we needed to settle the particulate, they had 4 ponds. Once we put in the flocculant treatment, there was no additional improvement in water quality with the remaining ponds, so we really could decrease the space and the ponds that we needed to settle out the particulate. So with that, I want to move on to nutrient treatment. This is, we have a pond line where we actually in some states use the flocculants directly in ponds and lakes to remove phosphorus and turbidity. And so what we call these is the pond logs, and again, the nutrients that we're primarily targeting are phosphorus. So phosphorus can cause eutrophication, and which can lead to excess growth of things like algae and aquatic plants. And anionic PAM and flock logs can be a really great solution for helping to remove some of that excess phosphorus so that we can improve water quality and clarity. So the nutrient removal with the flocculation, typically it depends on what type of phosphorus that we are working with. Again, we typically can target around 95% of turbidity reduction, but for phosphorus, we would normally see rates of total phosphorus removal on average somewhere around 70%. So just like with turbidity and metals, we use the flock logs or the pond logs. We need mixing, reaction. The polymer has to dissolve, disperse through the water column, bind with the material in the water, form those flocks, and then it'll settle to the bottom of the pond. In order to get enough mixing and reaction, we need to use this in conjunction with things like aerators, fountains, again tied off into the flow, waterfalls, and also, so here we have our aerators, our fountains, our waterfalls, circulators, anything that can get vigorous moving and mixing so we can get flock forming, so we can remove the particulate from the water column. An example of this was at Hillman Lake in Florida. This was at the Reedy Creek Water Management District, which is essentially Disney World. So it was a 2.5-acre stormwater pond. During the course of this, it was circulating 3 million gallons at about 347 gallons per minute. We did it for about 3 years. They used a solar-powered aerator called a Solar Bee. We had this was monitored by the Florida Department of Environmental Protection. We tied the flock logs off to the sides of the Solar Bee in an area where the water could move and flocculate around them. Again, the polymer in log form can be added to anything that can get the water moving and mixing, and we're trying to remove nutrients, excess phosphorus in this case, so we can improve the water quality. So before treatment and after treatment, we're not removing all of the phosphorus. We decreased it by a significant amount, enough that we're able to cut out some of that excess vegetation growth due to high levels of nutrients in the water column. So now we've done metals and nutrients. Another really useful and effective and really cool use of the anionic PAM is sediment management, or what we like to call thickening or demucking. And what this application is the anionic PAM that we use for water treatment and erosion control is water soluble, and it dissolves in water. However, it does also hold a bit of water. And so what we can do is when we have, say we've dewatered a basin and we have very high water content sediments that are soupy and difficult and expensive to manage and remove, maybe we're cleaning out sediment basins, you can apply the granular form. Again, it's site tested. We still do a sample analysis to make sure it reacts and works, but we can apply it to the sediments, mix them in as what they're doing right here, and mix them in, allow them to sit for about 20 minutes. And then what happens is it will solidify those into a very manageable material that can be easily picked up and hauled away. So you can put it in and haul it off sites. That's as long as the sediments themselves aren't contaminated. There's no special disposal considerations with the polymer. It's non-hazardous, so this can be a really cool application to help save time and money when dewatering basins and removing and cleaning out basins and things like that. What we can do now is that demucked sediment that now is treated with that anionic PAM, it makes a very effective soil amendment that can be used to help establish vegetation. Now it's got a polymer in it that has benefits of helping establish vegetation, holds nutrients, and so it works really, really well. You can use it for erosion control on other areas of the site, and again, use it as an amendment. An example of when we did this type of application was at Croft Pond in Nashville Zoo. They were redoing their swan exhibit. You can see that they didn't have really great access for their machinery on this specific site. And so what we did is we used the silt stop granular to thicken the sediment so that it was more manageable and easier to get in and remove it. You can see the type of muck in the bottom picture that they were working with. So it's a relatively low amount. So we're using about 50 pounds per 100 to 200 cubic yards. So to do this whole application, they used about 5 bags or 250 pounds of silt stop to demuck the pond. It was extensive cost savings on the amount of time it took them to complete that project. Another benefit is once they have cleaned out the pond and they're refilling it, there's some residual PAM in those sediments. And what they do is they often can prevent a turbidity bloom when they are refilling that pond. So this next application isn't necessarily demucking, but it was adding the granular PAM to some kind of waterlogged soils and shows the effectiveness in helping to establish vegetation. So this was a Florida stormwater treatment. It was a pond application. They had sandy soil and they were looking to establish vegetation in this stormwater pond that was going to be used for nutrient removal. So what they had done is they went in and installed about $10,000 worth of native vegetation in the 2 weeks before the rainy season here down in Florida. You can see the vegetation that they've installed in these images. And after a light rain event, they already had soil erosion occurring, sandy soils down in many parts of Florida. You can see some channelization there, and they were very concerned that they were going to lose soil and these expensive plants that they installed in this basin as their kind of future nutrient control. So what we did is a hydromulch and PAM application to hold the soil in place and help the plants establish roots so that they could kind of hold their own during the rainy season when we start seeing these bigger rain events. One of the cool things about this application is that we completely covered the soil and the plants. There was standing water when we applied this in many areas of this basin. So now we have our rainy season in Florida. One of our team members, Eddie Snell, he worked for Disney for many years using anionic PAM technologies to manage their stormwater, and And so this was one of the projects that he was working on. And so of course we're including our Disney picture with the storms beginning. So we get a 2-inch rain event and there was no soil or plant loss. So that hydromulch application, again, a light rain event was forming those channels all through this stormwater pond. And with that hydromulch application with the PAM to help hold all the particulate and that soil and plants in place, there was essentially no soil or plant loss with a very heavy rain event. We had rapid plant germination. Again, if we think back to some of the earlier presentations in this series, the United States Department of Agriculture has been using and promoting and researching anionic PAM for over 50 years now, and they are and it is promoted to help improve crop yield because, again, it's holding nutrients, bacteria, seed or fertilizer if you use it, the soil, all the things that we need for plant growth, improves infiltration in the soil, improves soil structure. It's just a very beneficial amendment to help with plant establishment and growth, which is why it's such a great amendment for erosion control and hydroseeding when our ultimate erosion control goal is to establish vegetation. And so we're seeing that in this project as well. Rapid plant germination, the plants established and the pond stabilized in half the estimated time. So again, this probably took a very small amount of polymer, probably a bag of polymer or less to do this whole project here. And so a little bit goes a long way, and it has a really great benefit with those other BMPs like the hydromulch. So now I want to move on to dust control. So this is a really common application. So this is typically for dust control. If we're in drought or areas with high temperature, dust is of course a form of erosion, and we are responsible for keeping that fugitive dust down and our soil on site. And so dust control is a very important application. As you can imagine, water is the most common form of dust control. Unfortunately, again, if you're in a very dry area or a hot area, that water evaporates very quickly. So it's labor intensive, water expensive, it's continuous and temporary. Another common type of dust control are things like metal salts, like magnesium or calcium chloride. Those are common. They're hygroscopic. They hold water and kind of form a crust, and they hold water in the top layer and help keep dust down. The thing about the salts is that they can increase salinity in receiving systems. I'm from the Midwest. I'm up in the Upper Peninsula of Michigan. It's a little bit too cold up here in the winter for salt, but downstate and some other areas of the Midwest, they have some issues with all the road salts increasing the salinity in the streams and receiving systems. And so what anionic polyacrylamide offers is a very effective, PAM is also a very, very common dust control application across the United States and Canada. And so then it's also a non-salt option. Again, what it can do is it can hold the soil particles on the surface, increases that particle size, also holds some water like we saw in the demucking application. So it's going to decrease the watering frequency that's required. For dust control, we can use both the 600 and 700 series, so the liquid PAM emulsions, and also the granular. The granular and the liquid both need to be mixed into a water truck or a hydroseeder and sprayed on the soil surface. Common applications would be things like haul roads, waste piles, tailing piles, construction sites. The lifespan of these applications is, typically, a week to upwards of a month. Oftentimes we say if it's a haul road or a disturbed site, then it might be, less than a week. If it's undisturbed, certainly a month or more. A great example that comes to mind is, again, down at Disney World, there was a haul road that was leading to a landfill, and dust from this roadway was was blowing onto a very high-end resort nearby. So there was a lot of complaints. It was covering cars. And so what we went in and did is a single application of the granular PAM. We mixed it into a water truck and applied it to the surface of this roadway. And that single application, they were watering 10 to 12 times a day before the PAM application. So 10 to 12 times they ran the water truck over this road to keep the dust down. After the PAM application, it doesn't completely remove the need for watering, but they needed to water that site only one time after that one application of PAM. They watered the road every single day, and they did not need to reapply the PAM for 45 days. So the lifespan can really vary, and so that one application lasted for 45 days, but they watered daily. And so it depends on the application, but it's a very effective way to decrease your water requirements when you are keeping dust down. If it's not on a roadway and you're applying it, it's going to aggregate those soil particles and hold them in place. And so that also likely won't need multiple reapplications. Again, as I mentioned before, that concentrated liquid emulsion can be added, as well as the granular, and when those are applied, we can improve the water, the air quality, and keep that dust on site. So the last application that I wanted to go over is probably the least known in terms of what we do with anionic PAM. If you remember from the first or second presentation in this series, we talked about some of the benefits of anionic PAM for passive treatment. And one of those is that it works in a really wide range of pH, and it does not change pH. And so this application that we're talking about decreasing pH with anionic PAM might sound contrary to that. But what we're doing is we're not decreasing pH and chlorine using the PAM. We're using the PAM as an environmentally friendly passive delivery system for other low toxicity materials that we can deliver using the PAM, so we can manage some of these other water quality issues. So again, we do pH adjustment. We currently only do pH decreases with what we call our pH down logs, and we also do chlorine neutralization. So the way that works with the pH log specifically, we use anionic PAM as well as food grade acids, very weak acids that can decrease the pH. Just like the metals and nutrients and turbidity removal, it has to be used in flowing water so it dissolves. In these cases, the mixing's not quite as important. We want to make sure we're mixing so that we're equally distributing the log components so that we're evenly decreasing the pH, but we're not trying to form flocks. So those mixing requirements might be a little bit less for the pH log. Again, the type of pH that we're only trying to make small pH adjustments. So typically, we're not going to take a pH of 12 and drop it to 8. In most cases with this technology, we're usually looking to drop it 1 to 2 units because we're using very weak food grade, safe to handle acids. And the reason for this is that we're replacing some of those more dangerous and bulky strong acid chemical feed systems. So for example, there was a mining site up here in the Upper Peninsula of Michigan. They had a natural river that was leaving their site with a pH around 9, and I believe they needed to be at 8 or 8.5. And so in this water, we used the pH. They had a totes of acid on the banks of this natural river, and it was just too much of a hazard and too much of a risk, and so they wanted to find another solution instead of having a tank of acid on a natural river in a remote area. And so we decided to use these the anionic PAM as a delivery in these pH logs, and so they worked very effectively. We were able to decrease that just the slightest amount that they needed to meet their discharge requirements, and we were successful. And so that's kind of the purpose of the pH logs. Another example of that was a tunnel construction in Georgia, which is where Applied Polymer Systems is based out of. So this was the processed water required treatment during this before it was discharged to a trout stream. It had high turbidity, and it also had a high pH. And we also had a very small treatment system footprint. So in this case specifically, we added flocculants with a tank and got our mixing and reaction and used the tanks to settle the flocculated particulate. We called it a launder system. So we treated the water with the pH logs and the floc logs, and then used the tanks to settle particulate. Excuse me. So in the first picture here, you can see the ropes, those jute ropes, as it's dumping over onto some flocculant logs, and we're getting our initial dosing of the pH logs. The polymer blocks were matched to the discharge water. The pH adjusting blocks do not need to be matched to the water. They all contain the same acids, but if we're removing particulate, in addition, we're going to use other types of floc logs that have been matched to the turbidity in the water that we're trying to remove. So we used a combination of pH logs and floc logs for this particular site. Tank 1 acted as a settling basin to capture the large particulate, and then we had particle curtains and additional settling in the final 2 tanks to capture any finer particulates that had released. There was still a little bit of turbidity leaving the 3rd tank, and so we discharged it over a few additional polymer blocks in this small basin as a clarifying step, and then discharged the water, and you can see the final clarity there. So we were able to discharge it within the goals for turbidity and pH for that project. And then the final piece was chlorine neutralization. Again, just like with the pH log, anionic PAM is not going to neutralize floc, affect chlorine really in any way. But we use other low toxicity types of materials that are able to neutralize chlorine, and we use the polymer as a delivery system. So we're able to we typically use this now for things like municipal swimming pools when they need to empty them and clean them out, things of that nature. During COVID, there was an increased demand for this type of technology, again, because we were disinfecting, parking lots and really everything, in the early stages of COVID. And so they wanted a passive way to neutralize that chlorine before they discharged it into some storm drains and areas where they were disinfecting buildings and parking lots. And so that was what we used the chlorine log in those points. Again, it works in flowing water. The mixing and reaction isn't as important to form floc, but we still want to make sure that the materials are evenly distributed and reacting with the chlorine in the water. It works in minutes or less. We need a little bit more mixing time depending on what your initial chlorine is. And again, this isn't nearly as widely used as the other technologies with PAM, but it just highlights the versatility and the many different uses of the PAM technology. And again, the reason that we're able to do all these different things is because the PAM is so effective at binding particulate, and it has that low toxicity, which makes it able to be used in so many different areas and application. So just to recap, product capabilities with APS, we're able to stabilize or remove many different types of particulates and constituents. So we stabilize and remove sediment, phosphorus, nitrogen, not so much. There have been quite a few studies, especially in agriculture sites, where anionic PAM is very, very effective at preventing the runoff of nitrogen on soil surfaces and in soils. It's not as effective at flocculating nitrogen in water, but it works really, really well to prevent nitrogen loss for erosion control and as a soil amendment. Of course, we can also remove metals and also hold those in place in soils by holding the soils in place. Again, nutrient, chlorine, and pH. It's not the polymer doing it, but it's just a cool way that we've been able to implement this technology. So with that, again, there's the granular form, erosion control, water treatment, that's silt stop. The flock log and the pond log are those hydrated forms of the log that dissolve in flowing water, turbidity, metals, nutrients, and then the granular forms we can use for both water treatment and erosion control. What we want to make sure we're doing is all of the polymers that we've talked about in the last 3 hours are NSF standard 60 certified, meaning that these polymers meet drinking water standards. All of the polymers that you use for erosion control and stormwater should meet drinking water standards just in terms of safety and quality. Most states and EPA guidelines require that. Also, anionic PAM, safe for fish. Make sure that all products, all anionic PAM or any flocculants or chemical treatments that you're using for these types of projects have been fully toxicity tested. At APS, every single product that we have has been toxicity tested by a third party according with EPA guidelines, acute, chronic, 2 species, very, very thorough. And then again, you want to make sure that that our products are site specific and you're matching the polymer to each site's soil and water.